Welcome to this lecture, briefly covering the topic of other expert system variants. In previous lectures, we've largely focused on rule-based expert systems, but now let's take a quick tour of some other kinds of expert systems that have been proposed. These include fuzzy expert systems, which apply fuzzy logic using rules, frame-based expert systems, which rely on frame representations, and hybrid expert systems, including neural expert systems, which combine rules and neural networks, as well as neural fuzzy expert systems, which combine fuzzy rules and neural networks. On this slide, we've reproduced a table from a 2014 paper comparing the different types of expert systems we've mentioned thus far. First off, rule-based expert systems use the standard rule representation we're familiar with. This gives them a high explainability, but a number of limitations in terms of learning, flexibility, adaptability, maintainability, and tolerance to imprecision. Differently, fuzzy expert systems generally rely on rules that employ fuzzy logic, that is considered to be well suited to handling uncertainty. They also are considered to be quite explainable. However, there are trade-offs between relying on human-intuitive linguistic variables and the potential for a lack of precision in explanations. Beyond this, they suffer from many of the other drawbacks mentioned before for rule-based expert systems, and they can be particularly difficult to maintain. Frame-based expert systems are recognized for their maintainability, but are not well suited to handling uncertainty, imprecision, or knowledge updates of any kind. Further, we have neural expert systems, which combine if-then rules with a neural network representation that is better suited to learning, adapting, and being tolerant to uncertainty, but at the drawback of more limited explainability. And lastly, neuro-fuzzy expert systems, which have similar advantages and disadvantages to neural expert systems, but also include the negative trade-offs of fuzzy expert systems. Here we've briefly pointed out a few distinguishing features of each, but feel free to pause and examine this table more closely, as well as check out the original paper for more details. Let's begin with fuzzy expert systems. As some background, let's start with some fuzzy logic basics. In brief, fuzzy logic refers to logic that describes fuzziness, or in other words, that describes vagueness. Here, decisions are based on a degree of membership, rather than a Boolean yes-no or absolute true-false. So in other words, these are systems that are meant to deal with uncertainty. Here, all things are described on a sliding scale of inclusion that suggests the possibility that a given statement is true or false. So again, instead of a Boolean yes or no, we have a quantitative grayscale indicating degree of membership in one group or the other. Each fuzzy term value of a rule's antecedent or consequent can be represented by what is called a fuzzy set, which can also be described by a linguistic variable. In this example, our fuzzy term is A, and A can have a degree of membership x that can range from 0 to 1. Here, our term A is 1 if x is totally in A. It's 0 if x is not in A, and more commonly A is between 0 or 1 if x is partly in A. One way to capture this idea is thinking about membership in groups defined here as being short, medium, or tall. We might say that anyone over 200 centimeters is clearly a person who's considered tall. In other words, they're totally in membership A, or we'd say A is tall. However, as we go down in height, at some point it's less certain that we might call someone tall versus medium height. At 170 centimeters, some people might consider that person tall, while others might consider that person medium height. So this is all about trying to capture the degree of membership based on the probability or certainty that you belong to one group or the other. Now let's look at some fuzzy rules. Here's a classic example of an if-then rule using binary logic. Rule 1 says, if temperature is greater than 30, then the fan speed is set to 5. And Rule 2 says, if the temperature is less than 10, then the fan speed is 1. A similar fuzzy rule using fuzzy logic might look like this. If temperature is hot, then fan speed is fast, and the second rule being, if temperature is low, then fan speed is low. Notice that these rules are now defined in very qualitative terms rather than precise quantitative ones. When it comes to fuzzy inference, we have a mapping of a given input to an output using the theory of fuzzy sets. This happens in 4 steps. The first is called fuzzification. Here, given some crisp inputs, we determine the degree to which these inputs belong to each fuzzy set. For example, the crisp input might be the exact temperature, but a given temperature might belong to a different degree to different qualitative sets, based on the uncertainty of human perspectives as to what is cold, warm, or hot. The next step is rule evaluation. Here we take these fuzzified inputs and apply them to the antecedents. Then the next stage is aggregation of the rule outputs. Here we take the membership function of all rules consequence and combine them into a single fuzzy set that unifies the outputs of all rules. And lastly, defuzzification, where we transform the final output back into a crisp number or value. Notably, when we're dealing with fuzzy versus Boolean rule systems, Boolean systems that use AND would translate to a minimum in a fuzzy system, and a Boolean OR would translate to a maximum, and further, a not X would translate to 1 minus X. This shares some similarities with certainty factor propagation in conjunctive and disjunctive rules. Fuzzy expert systems can be particularly useful when we want to be able to express expert knowledge that uses vague and unclear words, like slightly overburdened, heavily reduced, moderately difficult, not so old, or very tall. Ultimately, fuzzy systems are relatively easy to develop, debug, and understand. However, they certainly have trade-offs as previously discussed. Now let's take a look at frame-based expert systems. Frames provide a structured way of representing knowledge that we'll cover more in another lecture. In short, knowledge is represented as a hierarchy, in other words, through inheritance. But it might not be immediately clear how such representations might be used to validate and manipulate knowledge. Frame-based expert systems do this using their methods and daemons. A method is a procedure associated with the frame attribute that is executed whenever requested. So you can think of a method as being represented by a series of commands similar to a macro in Microsoft Excel. And in general, daemons have an if-then structure, and they're executed whenever an attribute in the daemon's if statement changes its value. Here, inference involves rules serving the role of evaluating information contained in frames, and goals are established either in a method or a daemon. Next, we quickly examine hybrid expert systems. There are many creative ways to create hybrid expert systems. They can involve any combination of representations, or they can involve the integration of deduction with induction methods. However, not all combinations can be expected to work. Consider for a moment that we have an expert system that's been implemented to store and work with existing human expertise. Since it's based on human expertise, it of course can be flawed. So what if we want to update our system through ongoing experience? This is where machine learning or inductive learning could play a role in expert systems, by training a decision maker through examples rather than by simply pre-programming it. As a result, machine learning methods potentially have the ability to ultimately perform better than a human expert. One way to combine machine learning with expert systems is to hybridize expert systems with sub-symbolic systems. In other words, things like neural networks. The neural networks in this situation could be used to pre-process the data and then hand it over to rules, or they could be leveraged to learn better rules. Here's one example of a hybrid system. Specifically, this is an example of a neural expert system, or a neural network-based expert system. This starts with training data used to train a neural network, and you can also see in this figure familiar components of an expert system, such as the rule knowledge base, inference engine, and explanation system. However, in this case, rules can be extracted from the weights between the nodes in a neural network. Using a neural network might allow the system to deal with noisy and incomplete data better because of its generalization capability. However, because there are no guarantees about what is learned or the effectiveness of learning, or the translation of what's learned into a rule base, this can be at best viewed as an approximation of explainable reasoning. Another example of a hybrid system is a neuro-fuzzy expert system. While neural networks are low-level computational structures that perform well when dealing with raw data, fuzzy logic deals with reasoning on a higher level using linguistic information acquired from domain experts. As a result of the integration, neural networks become more transparent, while fuzzy systems become capable of learning. Each layer of the neuro-fuzzy system is associated with a particular step in the fuzzy inference process. To summarize this lecture, in addition to traditional rule-based expert systems, a number of other expert system variations have been proposed. which utilize alternative knowledge representation strategies, for example, frames or fuzzy rules, that can incorporate learning, for example, using neural networks, and that offer hybrid approaches such as neurofuzzy expert systems. Of note, all expert system variations have unique advantages and disadvantages that may make them better or less suited to a particular task or problem domain. I'm Ryan Urbanowitz, and thanks for joining me for this lecture. Stay skeptical, curious, and creative.